Hey folks, we are back. Back for another lecture on blood vessels. Another short little lecture, another 10-minute lecture. That's how we're doing things now. So what we got to do is pick up where we left off with arteries. Last time we talked about elastic arteries, muscular arteries. Now we hit the smallest of the arteries, the arterioles. Here's a cute little arteriole. He's not so big. He's not so big at all, is he? He's got a lumen. Can barely see his lining, his interna. He has a nice muscular media. But this one does not have an externa. They don't always have an externa, depending on how small they are. What is cool about these guys is they are highly innervated by vasomotor neurons. Vaso, vessel, motor, mover, vessel mover neurons. So these are sympathetic neurons that are going to have the capacity to change this guy's diameter. And thus, we're going to be able to regulate blood pressure and blood flow by changing the average diameter of our arterioles. So the tunica media of this guy, the muscle there, it has tone. The muscle in here is always contracting a little bit. It's never totally contracted, never totally relaxed. It's always somewhere in between. And this level of contraction is regulated by metabolites. So think about, for example, waste products, all right? Waste products from surrounding tissue cells will prompt the muscle here to have less tone. Why would that make sense? Well, if we have less tone, that means that the muscle's going to relax and the vessel's going to get a little bigger and a little more blood is going to flow, which if we have a lot of waste building up, we're really going to need a little more blood. Hormones are going to help us adjust the tone of the muscle, as well as the aforementioned sympathetic vasomotor neurons. So here we see an arteriole up here. There it is. We see a sympathetic vasomotor neuron. Notice how it has tonic activity. The neuron is always sending action potentials zoom, 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 down its axon, and that's causing the release of norepinephrine a little bit all the time onto this blood vessel right here. So this blood vessel is neither fully relaxed nor fully contracted. And what this does is it allows for twofold adjustment. Okay? We can have more signals on our neuron. And with more signals, we get more norepinephrine. More norepinephrine means the blood vessel is going to constrict and blood flow will drop. Or we could get less signals, less norepinephrine, and less contraction. The blood vessel dilates and flow increases. So here's another thing to remember. We have sympathetic neurons here. We don't have a counterbalancing group of parasympathetic neurons. That is why it is helpful that we have this arrangement where our sympathetic neurons start out with a medium level of activity. If you start medium, you can go lower or you can go higher. And that's what we can do. Questions. These, of course, will be done in class. More questions for class. But try and do them beforehand. So, boom, you can just kill them when I bring them up in class. All right, onward to the capillaries, the smallest yet most numerous of the blood vessels. They are the smallest, and not surprisingly, along with that, they have thin walls. This is the wall. It is just simple squamous epithelium, just an endothelium. That is it. There are billions of these guys, and they're high number, they're extremely high number, 10 billion or so, coupled with the exquisite thinness of their walls, makes them perfecto for exchange, for stuff going out and stuff going in. Heat, water, nutrients, wastes, gases, signaling molecules, electrolytes, the usual collection of things. We've got capillaries just about everywhere. Of course, we'll have more of them where we do more stuff, less of them in less active tissues. So there's three types of capillaries, anatomically speaking. There's continuous capillaries. They're the most common, but the least permeable. We have these abundantly in our lungs, in our CNS, in our skeletal muscles, in our skin as well. So here is the simple squamous epithelium. What I want you to notice is that in a single epithelial cell, I'm dancing on a single epithelial cell here, there are no holes in it. Now you might be thinking, what? Why would a cell have holes? But wait till you see the next two. The next two are going to have holes, okay? The next two types of capillaries. They are going to have holes. So no holes. There are going to be some spaces between cells. These spaces between cells are known as the intercellular clefts. All right, number 2, fenestrated capillaries, found in our kidney, where, of course, we're doing filtration. I mean, what is a filter but something with lots of little holes in it? And here are the little holes, little endothelial holes. Fenestra, Latin word, means window. So fenestrations are windows or pores. What would happen if you got defenestrated? See if you can figure that out. So anyway, kidneys got these for filtration, for making pee. We've got these in our choroid plexuses in our brain's ventricles, which of course I know you remember from AP1. That is where we make CSF, cerebrospinous fluid. We also have these fenestrated capillaries in our gut, in our small intestine. I mean, this is the place where we do all our nutrient absorption. So by having holes, we can have a little bit greater permeability, makes it easier for nutrients that have crossed the intestinal wall to then get into the blood. Okie dokie. Those are the 3 basic types of capillaries. Oh no, they're not. I thought I did all 3. I only did 2. And the third one here, the sinusoids. They're called discontinuous capillaries as well because there are big holes and big clefts. Sometimes these guys will actually have macrophages sitting in their lining, especially in the liver. That way the macrophages can help monitor the blood for undesirables. These guys, most permeable, but least common. So they're often found, besides we mentioned the liver, they're often found in bone marrow. Here's some nice bone marrow here. Here's some compact bone, and they ripped it off, and we see some underlying bone marrow. I mean, we're making blood cells in bone marrow. Blood cells need to be able to squeeze into the blood vessels once they're made in the marrow tissue. Gonna have these guys in the spleen as well. So any place where we gotta move big stuff. Okay? All right. Good. Now, we're done all 3. So let's talk about how we put these guys together. Because you're not going to have single capillaries. Instead, you have capillaries in beds. Why? Well, that increases their density, puts them closer to tissue cells. Remember, things are moving around by diffusion. If a capillary is not close to a tissue cell, it can't do exchange with it. By having these guys in beds, well, we can be closer. We can have more capillaries closer to tissue cells. We see our arteriole here. And this little guy right here is called a metarteriole. Then we get a couple options. We could zoom right through and skip the capillaries to get to the venule, the post-capillary venule. And if we zoom right through, we're going through what is called the thoroughfare channel. And that's what a thoroughfare does. It zooms you right through. But if we don't zoom right through, we could go through the actual capillaries, and those are the true capillaries there. Not really false capillaries, but you get the idea. All right, anyway, let's answer the question number 2 down here. What kinds of tissues will have high densities of capillary beds? Well, the answer is tissues that need a lot of blood. In other words, tissues that do a lot of stuff. Your liver, skeletal muscle, cardiac muscle. Those are demanding tissues. Kidneys, CNS, your brain, demanding tissues. And they'll have high densities of capillary beds. All right, what do you think aerobic training does to the density of capillaries in skeletal muscle tissue? I will leave you with that question. And thus concludes lecture number 2. See ya.